In this video, we're going to go over the BC 2010 number 6 question. So they give me a function f of x equals piecewise function cosine of x minus 1 over x squared, except for when x is 0. Can't put a 0 on the bottom there. And then when it is 0, it actually equals negative 1/2. So we're going to use that information and see if we can figure out what's going on here. So they give me a function. G is defined as 1 plus the integral from 0 to x, f of t dt. And part A, they want us to write the first three non-zero terms and the general term for the Taylor series for cosine about x equals 0. Use this information to write the first three non-zero terms and the general term for the Taylor series for f, so for that piecewise function about x equals 0. So it is technically Maclaurin because it's around 0, but Taylor covers all of it. So first thing they want you to do is just write the Taylor series for cosine. And that one, they would like you to just know from memory. If you want to build your list of derivatives, go for it. But cosine of x is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. It's the even one. It's the one that goes 2, 4, 6, 8 all the way up. It is alternating, so it's negative 1 to the n. X to the 2n is the general formula for that, and then all over 2n factorial. The pattern goes 2, 4, 6, 8. Who do we appreciate? But the 2 to the n, the 2 is the slope because it goes up by 2 each time. And if n starts at 0, if I plug in a 0 for n, it does give me a 1. X to the 0 would be 1. So that'd be where I would start. Then what I would do is I would just kind of break apart that cosine of x minus 1 over x squared. I have to look at the two differences between that and what a base cosine is. So it looks like I'm subtracting 1 from cosine. So I would actually do that first, and then we'll divide the whole thing by x squared. So I'm actually going to basically subtract 1 off of both sides. If you want to think about it as like subtracting 1 right here and subtracting 1 right here, essentially those cancel and that minus 1 on the left just stays with that cosine. So I've got that. Now I want to divide everything by an x squared. And this part can be a little bit tricky, but we've got the same equation as above. Now we're going to divide everything by an x squared. So essentially I'm removing a power from each of the x's all the way down the line. So basically this term I divided by x squared to get this. I basically subtracted 2 from the exponent. Same thing on this one. And then this x to the fourth term right here, I didn't really have the term before it, but I know it's going to be x to the sixth over 6 factorial. And so when I take a power of 2 off of that, that's how I get that x to the fourth over 6 factorial. The general term here is a little bit strange. I would say you could just subtract 2 from that exponent right there, but then you would have a negative power for x. So instead of doing that, we can just look at this equation and try to figure out what the pattern would be. Basically, we have like an x to the 0, so we go 0, 2, 4. That's the same as the 2 to the n. But the bottom there looks like instead of starting at 1, it starts at 2, so it goes 2, 4, 6. And so that 2n plus 2, I have to sneak in that little plus 2 right there to basically jump start the denominator, to bump it off, get it off by 2 from whatever that numerator is going to be. And for part B, they say use the Taylor series for f about x equals 0 found in part A. So I'll go ahead and just bring in what we found from part A. And they say they want us to determine whether f has a relative max or a relative min, or neither at x equals 0. So, and then of course give our reason. So I'm really thinking of that as my f of x function. And I'm only going to use the first 3 terms. They say use your answer from part A, and I had 3 terms there, so that all sounds pretty good. I could do the general term here, but I don't think I'm really going to need to. I'll kind of explain as I go why I don't think I'll need that. But if I'm finding relative max, relative mins, I'd first find the derivative. So I'm just going to find the derivative of that f of x. The first constant goes away, and I just did a power rule on the other 2. So 2 moves to the front, drop it by a power. 4 moves to the front, drop it by a power. So what I would do is just find the second derivative while we're at it. That'll make sense in a little bit, but I'm once again just doing power rule there. So I get 2 over 4 factorial minus 12x squared over 6 factorial. So for something to be a relative max, relative min, I want to first figure out, is it a critical number? So what is f prime at 0. So I'm just going to plug a 0 into that first derivative, and well, 0, they all have x's, so all of them go away. And that's why I didn't really need to use the general term. If I brought it down, it would have an x in it, and so when I plug into 0, it would still go away. So I don't really need to worry about the general term too much here. Now, once we know it's a critical number, because the first derivative equals 0, we have a couple options. You can try to build a table, a first derivative test table. Build numbers, plug in numbers right around 0, see if it's positive or negative, but I'm neglecting a whole bunch of terms. And so it might just be easier to do the second derivative test, and that is a test for concavity. Is it concave up or concave down? If I know it's a critical number and it's concave up, that tells me it's a relative min. If it's a critical number concave down, I know it's a relative max. And then if it equals 0 or no concavity, the test fails in that scenario. So I just got to figure out which one it is. Well, if I just plug in a 0 into the second derivative, I get 2 over 4 factorial, and that's positive. Well, if I know that's positive, x equals 0, by the second derivative test, I know that's going to be a relative min. So I would say this is going to be a relative minimum. I've got critical number and concave up. Basically, it means that for the critical number, the slope is 0, and for the concave up, it's going to be a shape like this, and I've got my critical number right here, and so I know it's going to be a relative min. And for part C, they want us to write the 5th degree Taylor polynomial for G about x equals 0. So let's go ahead and do this. We can do a couple things here. The longer way would be to write all 5 derivatives that you're going to need here. So you could find the derivatives of those. We're going to do it in a slightly more efficient way, hopefully. So g of x is given to us as 1 plus the integral from 0 to x on f of t. So f of t is that function that we found from before. So I'm going to go ahead and bring that in, and I'm going to use t's for my variables because they do say with respect to t, and they did make that upper bound the x, so I don't want to double up on variables here. So I'm going to bring in that polynomial from the last part, negative 1/2, plus that t squared over 4 factorial minus t to the 4th over 6 factorial, and I can just anti-derive that. I can just power rule that. So for my g of x, the 1 plus stays the same, and then this is the power rule for each individual term on the inside. So the 1/2 gets a linear function, or 1/2 t, and then I bump up the other powers by 1 and divide by their new powers, and then of course I'm going from 0 to x on my bound. So if I plug in the upper bound x minus plug in the lower bound 0, I get 1 minus x over 2 plus x to the 3rd over 3 times 4 factorial, and then minus that 5th power. It's essentially that inside piece, but the x gets replaced on the inside. So that would be my function, my 5th power Taylor polynomial about x equals 0 to the 5th degree. And the last part here, part D, the Taylor series for G about x equals 0, evaluated at x equals 1, alternating series, decreases to absolute value of 0. So this lets us use the alternating series remainder theorem. That is, you get to use as many terms as you want, and whatever that first unused term is, that's going to be the max accuracy. It won't be off any more than that. So they want us to show that this is going to be, that the actual value differs by our approximation by less than 1 over 6 factorial. So let's first just bring in that P5 of x, our 5th degree polynomial that we've used in the previous parts, and they want us to find g of 1. So I'm just going to plug a 1 into that g. You can call it g of x here as well, but I like, if I'm using the polynomial, I like to use the p for this part. So they do say use the 3rd degree Taylor polynomial, so I'm going to go p of 3, plug in a 1, and so I'll plug a 1 in just to the first 3 terms. So I'm essentially plugging in just to those. So I'm going to kind of draw a line here, split that up. I just used the first 3 terms here, so I got the 1 and then minus 1/2, 1 over 72. That's the 3, 4 factorial multiplied out, and then just a common denominator. So 37 over 72 is my approximation using a 3rd degree Taylor polynomial for G. So the next part of this is, well, how accurate it is. Well, the full function value, g of 1, minus the polynomial approximation, that will give me my remainder, or my error, and that will always be less than or equal to whatever that next unused term is. So I went to the 3rd power. The 5th power is my next unused term. So I'm going to go ahead and plug in a 1 into that next unused term right there. So if I plug in a 1, that would give me 1 over 5 times 6 factorial. Absolute value of that is 1 over 5 times 6 factorial. That is less than 1 over 6 factorial. I've got that extra 5 on the bottom, so that denominator is bigger, which makes that fraction smaller. So it is going to be less than 1 over 6 factorial.